Thank you. Thanks for the introduction, Emil, and thanks a lot to Nick and Yosef for the opportunity to talk about ADS3 CFT2 from a slightly different point of view than some of these direct microstate or gravitational talks. I'll be going back and forth between bulk and boundary and trying to kind of cover, indeed, some of the big picture stuff here. Is this good mic-wise? People can hear? Yeah, okay. So I guess I should qualify this a little bit, because I won't talk about everything that's going on. And I'll just talk about aspects of ADS3 CFT2. And the original title for the talk was What's Going On Shell in ADS3 CFT2, because some of the things we've been learning about the correspondence hinge on this observation that we need to include more than just saddle points of the ADS3 path integral if we want to study pure gravity or something like it. And so there are questions about what to include, what they mean from the boundary point of view, and there's plenty of evidence that we need to consider such configurations. And because we're in ADS3, we have more power than in higher dimensions, and that will give us further insights, as is often the case in this lower dimensional setting. So there's a lot, to answer the question, how much is going on? There's a lot going on. And so I'll be focusing more on some aspects of the story which pertain directly to microstructure and microstates, as is the topic of the workshop, of the conference. So many of us are trying to understand the relationship between discrete spectra in, say, a chaotic CFT, which would be dual to some gravitational theory in ADS, where the chaotic spectra really starts to, the chaos of the spectrum really starts to onset in this high energy regime where we're talking about black hole microstates here. So maybe this is above some sort of black hole threshold. And sort of what the relationship is between the things, between this and the things that we seem to see in gravity most easily, which are smooth curves like that, right? So going back and forth between these two pictures as much as we can on both sides of the duality is our goal. Right? And so one of the messages of the talk is that off-shell geometries in ADS3 seem to be what capture the random matrix dynamics in 2D CFT, which is to say, if you like, the statistics of this discrete chaotic spectrum, but in a way that can be codified using the language of random matrix theory, suitably generalized to 2D CFT. Now the talk won't just be about off-shell stuff, because, well, first one needs to talk about on-shell stuff to set the stage for that. And there's been a lot of progress in understanding the ADS3 path integral in the on-shell setting, and so I'll also talk about that. So let me give an outline. First, there will be some prehistory whose goal is to get everyone on the same page, but also to explain from whence the random matrices came in this story. Okay. Then we'll have a little bit of a kind of phenomenological excursion into an off-shell zoo of possible geometries that one should consider. Then we'll be able to talk about some modern approaches to the ADS3 gravitational path integral, and I'll focus on 4 different threads that you likely have heard about, and their interrelations, what I think are the open questions for each, and then try to say something about just purely on the CFT2 bootstrap side, what kinds of questions I think we ought to ask in this next generation of bootstrapping to understand black hole microstates. I'm hearing some funny feedback. Is anyone else hearing that or not? Yeah? Okay. I don't know what to do about it because I'm going to keep talking. But yeah, I feel like when I'm near the board and I say some stuff, it's not getting crazy, but I'm just going to note that, and maybe this can be fixed. But anyway, is this size writing good for people? Oh boy. All right. Okay. So, some of this is stuff that you've surely heard about, but everyone here is coming from a different background. It's a conference with a nice, diverse set of participants, so forgive me if some of this is sort of well-trodden territory, but I think it's important to make sure we're all understanding what I'm going to try to say. Okay, so first, the prehistory, which will lead us to some papers from 2020 by Maxfield and Teriachi on the one hand, and Kotler and Jensen on the other, which really emphasized that there's some random matrix stuff going on in the near extremal spectrum of 2D CFTs, and that off-shell geometries are important to understand that. Those were the 2 main messages of those papers. So let's build up to that. Okay, so first, back in 2007, Maloney and Whitten wrote this paper in which they tried to compute the ADS3 path integral with torus boundary conditions in a very natural way. Okay, so they did the first thing you would do if you have a set of saddle points in a semi-classical expansion, which is to sum over them and only them. Okay, so this is a sum over smooth saddles. Gamma here, these are elements of SL2Z mod the subgroup which leaves the seed invariant. And what is the seed? It's just the empty ADS partition function. So this is the sum over all smooth saddles M. So these are 3 manifolds in the bulk, whose boundary is a torus. And that set of smooth saddles is ADS and all of the BTZ black holes. Okay, so the theory certainly includes those. And so the natural thing you might like to ask is whether the sum over just those gives you a sensible answer. Okay, the logic being that if you start including other stuff, then, well, who knows what to include? Okay, that was basically the philosophy. Now, famously, it turns out that this is unphysical, say from the CFT2 point of view, not quite for the reasons that they originally said, as we now understand, but later the unphysicality was made sharper in a way that I think is real. Okay. So this has a continuous spectrum when you extract the density of states of the 2D CFT. If you think about a large C theory and going to a large central charge and in some sense coarse graining over the spectrum, where maybe you expect e to the minus C type spacings at high energies, a continuous spectrum is not really a problem from that point of view, although at the time it was taken more seriously as a potential problem. But the real problem is that the spectrum is negative in a certain regime where it must be positive in a unitary theory, and that was brought to light more sharply in some work by Benjamin, Oguri, Xiao, and Wang in 2019. And this is where the near extremal physics comes in. So they noted that as you go to large spin in the density of states that you extract from this torus partition function, and you take the right moving dimension h to the semi-classical edge, that is where the semi-classical black hole threshold sits. And if you take it in a way that leave some coupling I'll call lambda fixed. So you take this difference times an exponential factor in the spin j entropy at extremality, where S naught of j is 2 pi times c minus 1 over 24 j. So this is the Carty formula evaluated at large spin. One of the sectors goes away and you just have this, so think of this as the extremal entropy in the spin j sector. So if you keep this thing fixed, so you go near extremality, exponentially close, in fact, then the spectrum is negative. And let me just write, instead of writing some equation for that, I'll draw a picture. So if we plot the spin j density as a function of the right moving dimension h, where delta is h plus h bar, and j is, say, h minus h bar, as usual in 2D. Then the density of states, if we start sort of at the threshold here, well, it goes negative and then goes positive, all right? And so this is bad. So this guy here, this is this exponentially small, exponentially close to the threshold region, but the density is exponentially negative there. Okay, so the integrated density, the total number of states which have a negative degeneracy is exponentially large as you integrate over this region, and that's not good. Okay, yes?
Is it worse of a problem actually than...
Gotta wait for the cube.
Is it worse of a problem than having a continuous spectrum, because both are non-perturbative effects? As in, this also vanishes as we send C to infinity, right?
Well, no, it's a good question. I think it is a worse of a problem, because after you integrate over this whole region, you're left with something exponentially large. So it's true that the window is exponentially small, but the amplitude makes up for that enough to give you an exponentially large negative degeneracy. So I think it's a little different than just talking about, say, a level spacing.
Well, we should not really trust integrals over regions that are exponentially small if we don't work in if we only have the leading term in an exponential expansion in C.
Yeah, so I take this to mean that that if you want to, that the solution of both problems might come from the same physics. Yeah, so I think the same physics ought to solve both problems, and indeed that's the kind of accounting for the actual random matrix fluctuations of this part of the spectrum. But so I think, yeah, I agree with the spirit of the comment, and I think it leads you somewhere that you want to go. Yeah. Okay. Now, so let us, in anticipation of trying to do better.
Sorry, do I understand correctly? The depth is e to the s naught, and the width is e to the minus s naught?
Yeah.
So there's of order 1 state there?
No, there's some, sorry, I might be getting these factors wrong, but when you do the integral, you end up with an exponentially large bit. Yeah. Yes. Yeah. Forgive the factors of 2 might be. Okay. Thanks. Yes.
Okay.
Yeah.
Oh.
Thank you.
4 versus 2.
Yeah. Okay, sorry about that. Good. So let's call our z grav, now writing it as a function of tau. So there's the sum over smooth saddles, which we certainly should include. And then now we know if this theory is to have a consistent path integral, at least in this sort of traditional sense, but where we want to correct this negativity and get something that's a bona fide partition function from the CFT2 point of view, then we need to have something else. Okay. So what is the something else? So there are seemingly 2 choices. Let me get some colors involved here. So the first is to not just sum over smooth saddles. So we can say we can add some non-smooth contributions. So geometries that have some non-smooth feature, some defect. Or we can add non-saddles, right? Or both. Now let's talk about the non-smooth case for a second. In ADS3, including, say, a conical defect is to be thought of as adding matter in the sense that a heavy particle back reacts to generate such a defect. And so there are other options besides adding conical defects, but non-smooth geometries can cure this issue, but you're retreating a bit from the actual original goal, which was to construct a pure gravity partition function without matter. The retreat is not a gigantic retreat. You're not adding light fields or stringy modes or infinite towers of states, but so that is to say the gap can be preserved at the Planck scale times some number, but it's still not the original theory that we're really after. Okay, but just to say a bit about these kinds of configurations, two kinds of options that have been talked about in the literature, in other words, cures for this negativity, involve adding conical defects with certain masses. That's work by Benjamin, Collier, and Maloney. And another, which Gabriele Di Ubaldo, my student, and I talked about last summer in a similar spirit, although with different features, involves adding a strongly coupled spinning string in the bulk. And in each case, one can cure this negativity in the spectrum. So a useful figure to keep in mind is what the spectrum looks like as a function of h and h bar. So what we're after in constructing a pure gravity theory is to have no states in these three regions, perhaps up to some exponentially small fluctuations there, and only having states up here. So this is where the black holes live semi-classically, and up to some non-perturbative corrections, that's what it would mean to have a theory of pure 3D gravity. A spectrum, which is you have a vacuum here I'm talking about the Virasoro primaries, and it's empty in these three regions, and black holes live here. Okay. So this line here is the line where the total conformal dimension delta equals c minus 1 over 12. And in each of these two proposals for how to fix this negativity, some states are added that are outside of the black hole region. So in this case, these are the conical defects. You have states, say, down here. They're order c, but visibly shifted away. I'm expanding this for visual aid. And then in this spinning string case, you have states that have the same twist, but higher conformal dimensions, so the gap is higher. But still, neither of these is pure gravity in the purest sense. Okay.
Once you begin introducing these string states, wouldn't it be natural to introduce also other string states that would... I mean, the conical defects are just, you introduce all conical defects and nothing else. But once you begin introducing strings, there can be other string configurations that it may be natural to add them, and then you have to decide why you add some and not the others.
Yes, so I think it absolutely would be natural to add more, an infinite set of them from a string theory point of view.
Yeah.
And what one wants to, so that I'd say two things. First, this is really just meant to be a toy model for that kind of more top-down configuration, which has some features that configuration ought to have, which is that the string scale needs to be of order the Planck scale, so that this was strongly coupled. And then if there are states with even higher dimension, then they will preserve the positivity, albeit giving a more complicated spectrum. So I think you can show that if you were to do that, if all the states are sort of above this state in the relevant sense, then it's still a physical partition function. But I agree that one would like to do something like that.
Can you explain why do you need the string to be strongly coupled?
Sure. So it's just essentially because we're trying to preserve a mass gap that is as high as the black hole threshold itself. And so if you look at the equations of motion for a string, such a folded spinning string in ADS, based on work of Maxfield and Wang, then you just look at the quantum numbers of that thing and you insist that when I give it this conformal weight, you just ask what is the tension, and it turns out to be strongly coupled. And that, again, this is like, this is what you would expect, right? G string tells us about the ratio of M string and M Planck. So this being order 1 is necessary if a string compactification is to give a pure gravity-like theory, because that means that there are no states up to the Planck scale. So the string states must be pushed up to the Planck scale.
Sorry, Eric, before you present the solution, I just want to make sure I understand the problem. So you want to find some low energy spectrum which after summing over images gives you a positive rho. Is that the problem?
No, not exactly. It doesn't need to be a sum over images.
Okay.
It's at this stage not completely clear what exactly one needs to augment this with.
Well,
but you want to
or
augment
change
it with
images or something, but in the, yeah.
such that when you treat this as a CFT partition function and do the inverse Laplace transform to extract the density of states,
Yeah.
it is positive everywhere and has a gap to the black hole threshold plus perhaps e to the minus c.
Okay. And those two conditions will more or less uniquely fix the answer?
I don't think so.
Okay. All right. That's
And I would say
that's
I'm not going to present the answer to the question.
Oh, okay. All right.
Yeah.
Thanks.
Wait, can I ask a very naive question?
Please.
I mean, how do you know you're not just papering over the cracks in an otherwise sick theory, in the sense of you filled up an obvious problem, but maybe there's some channel in some loop calculation or something which just reveals that this negative density of states is really there and it's just a sick theory?
I think at the level of density of states, you can answer that definitively, but I'd say that addressing this problem is more of a prerequisite for constructing a consistent theory. And
Yeah.
it could be that there's some other sickness. I agree with that. Yeah.
Okay, maybe we should move on.
Sure. Okay. So that was the option that I don't like, in the sense that I don't view this as a complete solution of the original problem, because we're adding matter, more roughly speaking. Where did I put the chalk? All right. The complete solution to the problem, at the very least, needs to give us a path toward asking where the microstates are in this theory, and that's something that requires us to reckon with, the discreteness of the spectrum, ultimately, and, say, the random matrix statistics of that spectrum. And this is a semi-classical fix, not a quantum fix. Okay. So instead, if we ask about the non-subtle option, then here's where the random matrix dynamics seem to come in. And so there were these two papers in 2020 that I mentioned, which gave us strong indications that this isn't just a schematic idea. The first is one by Maxfield and Toriachi, who argued that there need to be certain three-manifold contributions to the ADS3 path integral by thinking of the extremal limit as, in a dimensionally reduced sense, going to 2D using an effective JT description coupled to defects, and arguing that summing over defects in this setting is tantamount to performing a certain ADS3 calculation, which they demonstrated would cure the negativity. Okay, so I'm saying it that way just to make clear that there is not a bona fide ADS3 calculation that was performed, but what they argued was that in this near extremal limit where the negativity appears, the theory undergoes an effective dimensional reduction where you can use 2D techniques to do the computation. So what they showed was that in this sort of near extremal spin J regime, the density of states near extremality undergoes a shift, whereas semi-classically, the spectrum starts here. They derive from this point of view a shift in the location of the threshold, which is exponentially small in the entropy. So there's a -1 to the j, and e to the minus s naught of j over 2, or this, again, was this extremal spin j entropy. So this is, right, this is like e to the minus square root cj. So this is exponentially small. But the corresponding density of states above this threshold is positive. And they encouraged us to think of this negativity problem in the 3D gravity path integral as not including all the stuff you need. And in fact, this is some artifact of truncating the expansion of this in the entropy. Okay. So this thing is supposed to be a 3-manifold with torus boundary. And they then assert that the relevant ADS3 gravity calculation one wants to do is to compute the partition function of Seifert manifolds. These are smooth 3-manifolds, which should be thought of as circle fibrations over a disk with orbifold points. And so they are smooth from the 3D gravity point of view. You can think of them as you start with your solid torus, and then you cut out some solid torus within, and then glue back in after doing an SL2Z transformation. And you can do this lots of times and make lots of different Seifert manifolds. And these are the uplift of these configurations here. And so doing that in some SL2Z invariant fashion, including all the relevant Seifert manifolds, should give this shift, thus curing the negativity. Luca.
Just a quick question. In 2D,
Yeah.
there was no negativity to begin with.
Yeah.
So in the near extremal limit, if you just view it from a 2D perspective, there was nothing that needed curing.
Right.
So isn't that a bit...
Are you questioning from the 2D point of view why one should include these off-shell defect configurations?
No, I'm asking from the 2D point of view, why wasn't it, if the 2D thing was so exact that we could trust including these off-shell configurations, why weren't we seeing the negativity to begin with from a 2D perspective?
Let's see. So from the 2D perspective, this just shifts the edge of the spectral density in the random matrix ensemble, right? But the negativity arises from, right? Indeed, there's no negativity until you start with a 2D CFT with left and right movers, and you zoom in on this region. So, yeah, I think the motivation to add all these off-shell defect configurations in the JT setting really comes from the higher dimensional point of view. Yeah, I think if you were just working purely in 2D, like the reason you'd want to do that would be different.
Yeah, so a comment on this is that there is an analogous problem for the negativity, but not in pure JT gravity, but in JT gravity with defects. So if you sum only over one defect, so genus 0, but you include only one defect, then the density of states you get has this negativity. But then once you sum over all defects, you solve it. So the analogous problem will be, not accounting for all defects in JT with defects. Yeah.
Okay, so the second, and so this argument, even though they didn't do the ADS3 calculation, just to make my perspective clear on this, they didn't do the ADS3 calculation, but I think the physical argument is very convincing. Okay. As is the calculation, which is valid in a limited regime of validity.
Okay. And these are non-saddles because there's no hyperbolic metric in this topology?
Yes, thanks. Second, around the same time, and one of those things that sometimes happens, the Cutler-Jensen paper came out. They studied a different quantity. namely an ADS3 wormhole with two torus boundaries and sort of trivial topology in between. So sometimes think of this as torus times an interval. So this has no hyperbolic metric, but using the boundary graviton techniques, if you like, they computed the gravitational amplitude for this geometry. And there were parts of the computation that were unfamiliar, possibly somewhat ad hoc, but the result was really on the nose with expectations from a physical point of view, and I'd say has been since strongly justified from other perspectives, which we'll talk about in a second. So what is the answer that they computed for this thing? So it's a function of tau1 and tau2, one on each boundary, and up to some factor, something like 1 over pi. This takes the following form. So if tau I is xi plus I, so y is im tau on each boundary, the answer takes the form y1, y2 over y1 plus y2 plus a bunch of stuff. And this thing here is the ZZ correlator, the two-point function in random matrix theory, and double-scaled random matrix theory. Okay. In particular, if you analytically continue y1 and y2 to go to the spectral form factor kinematics, we take y to be beta plus or minus it, and you go to large T, this is what is responsible for the linear ramp. Okay. Now it's got a linear ramp. Okay. Good. So the reproduction of this sort of universal answer from random matrix theory, namely the thing that people refer to when they talk about random matrix universality in the simplest setting, the fact that this amplitude reproduces that, plus a bunch of pieces that are needed to have a modular invariant, conformally invariant answer, gave some sort of beautiful confirmation that random matrix statistics are somehow hiding inside the spectrum of the dual CFT, even if at the time it wasn't clear exactly what this randomness was, how to quantify it, and which part of the spectrum it's living in. But that's what we have since tried to understand better. Okay. So, any questions about this setting the stage?
The logic of summing non-saddles seems completely insane. Is there another example in physics, not the 3D pure gravity, where people sum over non-saddles and get sensible answers? And I'm not talking about solving exactly the path integral, but summing non-saddles.
Well, in any situation where you don't have a semi-classical expansion, then organizing things into saddles is, at the outset, not justified. So that is one common setting. Maybe your question is more along the lines that what we're after is a semi-classical expansion of this path integral, and so why aren't the saddles enough? And from that point of view, one point I want to make is that, kind of from indirectly speaking, this thing is not mysterious from the point of view of the problem that we're trying to solve. Think of this as defined by this difference, right? If the pure gravity path integral exists, then there needs to be something else, and we call that something else off shell, and we call it that because we're trying to study pure gravity and we don't want to add matter. So at this point, that's just a name for something we evidently need to add. And then you can talk about its geometric manifestation, and then indeed we lack classification, as I'm about to say, although I think that's already obvious.
But my question is, let's switch the topic. Is there another example in physics? You sum over non-solutions and you get a sensible physical answer. Can you name one example?
Well,
I'm criticizing the logic in two non-saddles.
Yeah. Did I give it a thesis defense? Let's see.
Constrained instantons are another example.
Yeah, and so that is, of course, what
What they did.
Of that.
But there's for instance, a calculation by Gregory Harvey and Moore of strings in KK monopole geometries, if I'm remembering correctly, or maybe it's computing the partition function on the cigar, something like that, where they're looking at some property of fibranes and they need some instanton correction to the geometry, and there are no non-perturbative corrections in alpha prime that are legitimate Euclidean instantons. So they have to, there's some zero mode basically that they have to freeze and find the instanton with that frozen zero mode and then integrate over the zero modes. But without freezing the zero mode, there's no classical solution. And a very similar technique is being used here. If I'm remembering correctly, it's that the size at the minimum of this interval in there is something, is the reason why it fails to be a classical solution. And you still have to freeze that circumference, and then there's a solution with that thing frozen.
Yeah.
And then you need some measure for integrating over that cycle length.
Right.
Right.
So in both of these examples, returning to your question and then returning to this because we're a little short on time, there are things that you might call almost solutions. And these are the ones that so far I'd say we understand best. I think the spirit of your question is a good one. And that's why we'd like to understand this classification better. Yeah. I'd also say, these excursions into complex metrics that are now things we newly understand and appreciate, those are things you might have rejected as non-saddles because for some unphysical reasons. And then is it really such a clean distinction between something which is a solution as if it violates some normal physical criterion versus something that's not a solution? I think that's not so clear that, those would also be outside of the remit of your question. So, okay. All right, now we have 25 minutes or something like this? Yeah. Okay, thanks. So this, I'm going to be quick here. All right, let's erase this. Here I just wanted to write down some examples of three manifolds that do not admit hyperbolic metric, so they are off shell, that are sort of fun to visualize, that we ought to compute the contributions of. Okay, so if you take a genus G Riemann surface with n boundaries times a circle, perhaps with not a direct product, but with some vibration, then, okay, this has a boundary, which is a disjoint union of tori. So there are n boundaries here. So manifolds like this may contribute to the path integral of interest. And so, for example, right, so if we take this is just the solid torus. This is just the disk times the circle, so the solid torus, so that's just ADS, or B2Z. But now if we take a torus with a hole with a boundary times a circle, so this is, so now this was filled in, okay, so this was filled in now. This is just a 2 torus, and now we sort of add a hole, all right, aka a boundary, times a circle, and so here's the other circle. So these two together form the boundary torus, and so we can draw this sort of like that, where in here is some bulk topology hiding. This is like adding a handle, if you like, but you can't quite draw it as quite as simply as we do in the JT setting. But morally, that's the kind of contribution that this gives. Right. Now there are higher boundary versions of this. Okay, so the annulus times a circle. Well, this is just the Cutler-Jensen wormhole. Already, that was not on shell. But that is, in some sense, the leading contribution to the leading torus wormhole contribution. It includes exactly the ramp. But there are going to be corrections to this, where by corrections, I mean that there should be some e to the minus 1 over g Newton suppression of these amplitudes. We don't understand the systematics of that. But at the very least, there are topologies that exist that will give corrections, as you can see. So if we have some genus G Riemann surface and we add two boundaries, which I like to draw like this, times a circle, then it's like a two-boundary version of this with some genus G stuff in the bulk, right? So this is going to give us something which, if you like, corrects Cutler-Jensen with some bulk topology. Okay. So we'd like to be able to compute these kinds of things. And so, you know, how to compute those is still, well, this is work in progress. But for now, before proceeding to what we have learned in the past year or so about these modern approaches, I just want to say, you know, in short, if we pick some boundary two-surface sigma, then we should compute this as some sum over three manifolds in the bulk with the right boundary condition. And there's no classification of this. Okay. So we don't know which manifolds to include, and we don't know the suppression factors. So there should be some e to the minus c type organization of this expansion, but quantitatively, you know, rigorously, we don't know how to organize this sum in terms of some e to the minus c expansion yet, although progress is being made. From certain points of view, one expects an e to the minus c times the volume of this manifold to appear. And I think one can, yeah, I won't say anything more about that. So some of the guidance here, of course, is coming, I mean, needless to say, from the JT-RMT duality, where one has some sort of core manifold onto which are glued some trumpets to give you the boundary partition function. And so this thing has some volume, which famously is computed by topological recursion in the matrix model side, etc. And so what we're looking for is some 3D analog of this. Okay. All right, so, you know, a lot can be said here, but let me now transition to some of the really nice works that have come out in the past year or so. All right, so there are four that I will highlight, okay? So, I don't know how we want to do this. Let's see, let's maybe do it like this. So the first is this so-called large C ensemble. It was introduced by Chandra, Collier, Hartman, and Maloney. And so for each of these sort of 4 prongs, I'm going to maybe give one equation, explain what it's about, and then explain what it does and doesn't do. Okay, at the end, I'll try to say what I think the charge is for each of these approaches. Okay, so what these guys did was to say, for any on-shell wormhole in ADS3, we can compute to all orders in bulk semi-classical perturbation theory the partition function using a boundary ensemble of CFT data, which is given by some Gaussian random variables. So we treat the OP coefficients, we take the density to be Cardy, and we treat the OP coefficients as Gaussian random variables, and we compute contractions of these variables with that ansatz, and lo and behold, you reproduce the bulk path integral of some appropriate configuration, which is kind of the one you would guess based on what CFT quantity you are trying to compute. So what do I mean by that? Let me just give an example. There is an on-shell wormhole where the boundary is is not a torus, is a sphere, where you have 4, say, conical defects propagating from one boundary to another. And, well, with the benefit of lots of hindsight, which is common by now, you might say, oh, this looks like a 4-point function here and a 4-point function here with some correlation between the two. And so what they showed is that sort of the ensemble computes the average of a square of this 4-point function of these 4 operators, where this is decomposed in some OP channel, and then this Gaussian random ansatz is used to compute the contractions. And an independent calculation is done in the bulk, which gives the answer, which matches that one, and they both can be written in terms of some e to the minus Liouville action with some moduli fixed in the appropriate way. Okay. So this is probably familiar to pretty much everybody. Now, it's restricted to on-shell topologies, and it works. It operates one topology at a time. So there's no sum over topologies. And the way they constructed it, the ensemble is not fully modular invariant on average. It is S invariant on average. Experience with MWK and some other things that I'll talk about in a moment tell us that just S invariance actually is not good enough to really access all the relevant physics here. And indeed, once you impose full SL2Z, the corresponding ensemble is no longer Gaussian. I'll return to that in a second. So, for any boundary topology and for any on-shell wormhole with that boundary condition, this correspondence works. And so this is really a broad extension of what we could compute in terms of saddle point partition functions. But it has these limitations. And because of this, it doesn't probe this microstructure, or if you like, this randomness, certainly not in the spectrum, because there's no on-shell wormhole which is purely spectral, right? But even in the realm of the OP coefficients, it is computing some kind of coarse-grained information which emerges from some kind of randomness of an underlying ensemble, but the data itself is smooth and can be written in terms of functions which themselves are derived by crossing from the vacuum. So from identity block dominance in some channel. So this is of a very different nature than the kind of thing we were talking about before, which will really allow us to, in principle, access microstates. Yeah. So it's answering a different kind of question, I would say. Okay. Good. So this story was kind of axiomatized and extended by this second thing, which was this so-called Virasoro TQFT. This was discovered and worked by Collier, Eberhardt, and Zhang. And so from the point of view of this work, what this did was to sort of fully axiomatize and systematize for any such on-shell bulk 3-manifold M the computation of its partition function. So this is done essentially by understanding that while ADS3 pure gravity is almost Trent-Simons theory at the semi-classical level, it's not quite for famous reasons. For example, the presence of degenerate connections, which correspond to physical metrics. But a suitable reinterpretation and restriction of the solution space leads to a sort of TQFT approach to this theory, which can be written as a statement about, can be reformulated as a statement about the Hilbert space of conformal blocks in 2D CFT, and leads to lots of nice connections with surgery techniques, et cetera, in the theory of hyperbolic 3-manifolds. And so then, again, allows for a very efficient and indeed exact computation of the path integral for a fixed on-shell configuration. Okay, so again, any sort of number of boundaries, whatever topology you like, as long as there's a hyperbolic metric, this thing can compute it. And so one thing they demonstrated was that there's this 4-boundary wormhole with 3 defects on each boundary propagating symmetrically to the others. Whose amplitude gives some large correction to this ensemble, which indeed corrects the Gaussianity. You can view it as a non-Gaussianity of the OPE data. Right, so there's sort of 4 OPE coefficients here, and it gives some large contribution, which they can compute exactly, and can be thought of as a correction to that picture. But this story goes way beyond this example, but it's a nice one that they advertise. Okay. So I would say this is highly systematic. So it allows you to systematically access this picture of OPE statistics at high energy in a more robust way than that story. And these computations, even for a fixed manifold, can be viewed as valid at finite central charge. But for the same reasons as discussed here, because it so far is just restricted to studying on-shell stuff, and because there's no sum over topologies, it can't really address this sort of existence question directly in the way that we were phrasing it before. Okay. How much time do I have left?
A little over 5 minutes.
Okay, so let's hurry up. The third thing you need to know about is this random matrix tensor model. This was created by Alex Belin, Jan de Boer, Dan Jafferis, Pranjal Nayak, and Julian Sonner. There was a talk about this at Strings, which neglected to mention that, but those are the creators of this random matrix tensor model. And so this is a sort of from a different point of view as these. It's not a direct gravity calculation. What they say is construct something which treats the conformal data, the conformal weights, h and h bar, and the OPE coefficients as random variables more in the style of a matrix model, where there is some potential, whose job is to enforce modular invariance and crossing symmetry on average, in the sense of there being a small variance, which then gets taken to 0 in some limit. And there's some tolerance involved of that enforcement, and it's one of the interesting things is that you can then view this as starting from some space of approximate CFTs, and when you take the tolerance for the satisfaction of the symmetry constraints to 0, you're sort of zooming in on, say, bona fide CFTs, which actually satisfy these constraints. Whereas in these approaches, one is computing CFT stuff on the nose. It's not clear that you need to generalized to approximate CFTs to address these kinds of questions. But that kind of idea was motivated, say, in this paper by Schlenker and Witten, which tried to argue that the space of bootstrap solutions at large central charge might indeed be much larger than the space of CFTs that you would get by starting from finite central charge and going out to large central charge. And so in the same spirit, maybe approximate CFTs are indeed relevant for understanding semi-classical gravity. And this model tries to sort of make that concrete. Okay. Obviously, I'm just giving a sort of schematic discussion here for reasons of time. But just to emphasize some of the features of this thing. So it gives strongly non-Gaussian correction to this, kind of systematically corrects the ensemble picture. And it can be used to give you fully SL2Z invariant observables. And there's certainly an appeal to this sort of picture from the one lower dimension point of view, where there's a random matrix ensemble dual to JT gravity. Questions involve whether approximate CFTs really are the right notion for understanding this pure gravity question, what the relation is of this tolerance of violations of crossing to e to the minus c, for example. If the tolerance is exponentially small, then if you're trying to capture exponentially small effects, maybe taking the tolerance to 0 is at the very least subtle and might actually miss something. And it's not clear, again, that this can capture, so the big question I'd say is whether they can actually reproduce off-shell data. The claim is that with some very mild input, say a Carty density, that this can spit out not just on-shell partition functions, but even something like the Cutler-Jensen wormhole, or corrections to the MWK ansatz from off-shell stuff. That has not yet been demonstrated. I think there's some work in progress, but we'll see what that looks like. Okay, I don't actually know what they've computed. But that's the big question for them as far as the sort of spectral statistics are concerned. And finally, one approach that has tried to address this random matrix nature of the CFT2 spectrum more directly is some of the work that Gabriele and I have done, where we are exploring this idea of what we called RMT2, which is basically trying to answer the question of how you merge random matrix dynamics with the constraints, say Virasoro and SL2Z, of a 2D CFT, whose fundamental degrees of freedom, if you like, are not matrices. They are, CFT data. And so we developed a framework which, say, applied to the Cutler-Jensen wormhole, allows you to understand this very naturally. So in particular, the Cutler-Jensen wormhole can be understood as the minimal extension of the random matrix theory answer that's compatible with modularity and conformal invariance. So this amplitude can be shown to be extremal in the sense of the fact that all the corrections are just due to the extra structure of the 2D CFT problem. Something that would be nice to make more quantitative, but is true from the point of view of this trace formula we developed, which also allows you to understand this as emergent from some kind of coarse graining of 2 copies of a microscopic individual CFT. What we're trying to understand now is how to extend this beyond the ramp, if you like, to, say, lift a full random matrix theory ZZ correlator to the 2D setting. We're making some progress, but I can certainly tell you more about that offline. And it would be nice to make more concrete connections to, say, the kinematic or time scales in the 2D CFT at which this kind of diagonal approximation, which leads to this kind of amplitude, emerges. But we're making some progress there too. So, okay. Let me pause for questions. Obviously, I ought not to do that because maybe we're at the end. The original intention was to try to talk about some 2D bootstrap questions that are getting at the microstructure of spectra. Let's save that for coffee. And instead, I'll just, for each of these approaches, say what I think is the question that they need to answer, and then we'll conclude, okay? So for this one, I'd say in some sense it's been subsumed by the Virasoro TQFT, and yet for both of these, one can ask if there's a complete EFT for the OPE data. So if you can just completely systematically say for any given product or contraction of CFT OPE coefficients at high energy, what is the scaling with the entropy? The big question, as far as sort of circling back to these questions about existence of the 3D gravity path integral with torus boundary conditions, the question is, can the Virasoro TQFT formalism be tweaked or adapted to include off-shell stuff, non-hyperbolic manifolds? I think the answer seems to be yes, but let's see. Here, so there's some work that appears to be coming out, which shows that this thing can be shown to be equivalent to a sum over on-shell topologies in the bulk. But if one wants to go beyond the on-shell part, the question for them is, can they do that? How are the off-shell data produced by this model? And say, very concretely, can this model be used to reproduce the Cutler-Jensen wormhole amplitude? And more generally, can this model be shown to be equivalent to the kind of RMT2 formalism, which not only sort of explain this, but makes a prediction, which I didn't have time to discuss, for a piece of this Z off-shell with a single torus boundary. So I'd say, can this model produce that piece of data which we extracted by other means? And here, as I said a moment ago, I think we want to show that there is a more robust way to embed or lift random matrix theory to 2 dimensions outside of this sort of random matrix universal regime, if you like, sort of uplifting the full sign kernel morally, something we're working on. And so each of these touches on a different aspect of the ADS3 pure gravity path integral. And in conclusion, I would just say, I really think that the sort of random matrix part of this story is extremely important for understanding microstates, which everyone here wants to do. So yeah, for that we should try to be as limber as we can about the ADS3 path integral and actually compute some explicit contributions of this type. So I'll stop there.